Hi guys, welcome to the final part of materials. Here we're going to be covering internal forces, beam bending, and doing a couple examples. So the way we depict internal forces is that we're going to imagine that we're going to draw a bubble. We're going to break the beam and we're going to draw a bubble around it, the part that we want to focus on. So from here, we could draw like a broken down beam to see the forces inside this beam. And for this section, we're only going to focus on two types of internal forces. We're only going to focus on normal force and moments. Some notations on positive and negative. When we cut it, anything coming out of the beam will be considered a positive normal force, usually depicted by a curly N. As for the moment, we're going to do anything that makes our beam look like a smiley face as positive. Just note that we're going to draw these internal forces. We are going to always assume that our moment and normal force are going to be positive, and when we end up solving for that unknown variable, the positive and negatives will work itself out. So we're going to start off with it assuming that it is positive and do the math with equilibrium equations like usual, and we will get the correct signs in the end. I have a couple notes about moments. Moments are just another word for torque. We might have worded it differently, but it is exactly what torque is. So for this example, there's F1 and F2, and only one of these will create a moment. If you think about it, a moment is going to be whatever is perpendicular to your radius. As we learned in torque, or has a perpendicular component, if this is our radius, we imagine that to be our radius, F2 will not create a moment. It will be a force, it will have a normal force, it will affect the beam, but it will not affect the moment section when we're doing those calculations. In this case, F1 is the only thing that affects moments. Another thing to note is the placement where I cut my beam will matter with moments. Because moments is torque, which is defined as R cross F, the distance R will matter. For example, if I were to cut my beam here, so let me redraw it right here. If I imagine that this is 0.5, I'm going to draw my moment here. I'll call this M1, and I'm going to draw my force F1 here. So in this particular case, M1 will be going into the page. F1 will also be going into the page in this case, times 0.5 equals the sum of the moments, which is going to be equal to 0, because it's an equilibrium, obviously. So I get that the moment is equal to negative 0.5 F1 for moment 1. However, if I were to cut it further back towards the wall, I would do the same calculations, except for now, this will be 1 meter, for example. So in this case, our moment 2, the calculations are exactly the same, except instead it'll be negative 1 times F1. So the placement of the bubble matters in this case. This is also why if I were to push at F1, the place that the bar is most likely to break is towards the wall, because that's where the greatest moment is. So let's do a quick example of trying to find the internal forces of this beam. So we notice that the force is axial, so we know that there's not going to be any moments on this beam, so we know automatically that the total of moments is going to be equal to 0. So we only need to worry about normal force, and as we know with normal force, it doesn't really matter where we start our bubble as long as it encases what we need, which in this case is just the force in the right hand side. So we could redraw the beam. We are going to draw the force here, and we know that the internal force here is going to be the normal force, which I again depict by a curly N. So now all we have to do is write our equilibrium equations. So if you recall, equilibrium equation is going to be force in the x direction should be equal to 0. If we depict that going to the right is positive, then we know that force is going to be positive plus negative normal force. And if we solve for this, we end up getting that the normal force is equal to the force. As you notice, I wrote a lot more than we needed to find the normal force on this page, and that's because I also want to test if we could find the elongation of this beam. So let's start off by erasing the internal forces that we just solved for. Very well, but let us try finding the elongation now. So here I give you that the Young's modulus is that of aluminum, which is 70 times 10 to the 9 pascals, or 70 gigapascals, and the force, F, is going to be 40 newtons. So the first thing we want to do is write the governing equation. We know that Young's modulus is equal to stress over strain. We know the Young's modulus, and our goal is to find the strain in essence, because we know that we need to find the percent change of length to find the elongation. So first, let's try solving for the stress. The stress we know is defined as force divided by area. We know the force is 40 newtons, and the area that we're going to use is the cross-sectional area of the beam, which is going to be 0.5 divided by 0.5 divided by 0.5 meters squared, and that's going to end up equaling to 160 pascals. Oh no. We also know the original length of this entire thing is 0.5 meters. So how about we rewrite this equation real quickly? We know E is equal to the stress all over the percent length change, which is defined as the change in length divided by L, which is the original length. In this case, we could rewrite this a little neater, so we know that it's going to be the stress multiplied by the original length is equal to the change in length. We could further solve this. We're going to move this down here because we're running a little bit out of room. We know that the change in length is equal to the stress multiplied by the original length divided by the Young's modulus. We could plug things in accordingly. We know the change in length is going to be, we know the stress is going to be 160. The length is going to be 0.5. And the Young's modulus is 70 times 10 to the 9th. Plugging that into a calculator, I get that it's 1.14 times 10 to the negative 9 meters. That is a very, very small number, meaning that even with 40 newtons of force, it's only going to elongate very, very little.